Okay. Okay, so remember last time we did the first part of 6.3? Today we're doing the last, like the back half. All right, and then let me remind you real quick what the first part, so today we're doing the second part of the fundamental theorem. The first part said basically that integrals and derivatives are opposites of each other, which was a really big thing for us to discover. Basically, it said that if you take the derivative of an integral, then they undo each other. They're inverses of each other. Okay, that's part one. Part two says kind of the opposite. It says that if you take an integral of a derivative, then again, they undo each other in a special way. All right, so part two, there it is, okay. Here it is formally, but like I said, all you need to know is that if you take the integral of a derivative, you're basically, they undo each other. So here is formally, if f is a continuous function on a to b, whose antiderivative f of x is given by f prime of x equals little f, then the integral of little f from a to b is equal to the antiderivative at b and minus the antiderivative at a. And this word antiderivative means what it sounds like. It is what it is like going backwards from a derivative. Undoing a derivative is what antiderivative means. In other words, like it says here, if big F is an antiderivative of little f, that means that when you take the derivative of big F, you get little f. Okay, if none of those words mean anything to you, here's an example and then you'll see what's up. Okay, so this says take the definite integral from -2 to 3 of the function 6 with respect to x. Okay, so according to the second part of the fundamental theorem, all I have to do is get the antiderivative of this, then plug in this point, and subtract. All right, so antiderivative of this, the way to get that is you just kind of have to think backwards. You're thinking, what did I have to get the derivative of to end up with the 6? You guys know, you guys remember? Nice. What were you going to say? Yeah. All right, good job. Yeah, it should be 6x. Good job. That was pretty quick. Because if you take the derivative of 6x, you end up with a 6. Okay, yeah.
What about like in the case of 6x plus 1? Because like 1.
That's higher. That's really, really high level. And you are correct. And we will talk about that coming up. But you're right, that is also an antiderivative. That's why it says 6x is an antiderivative, not the antiderivative. That is really, really, really good thinking, though. So let me say something about that once we plug in some stuff, because you'll see we get the same answer no matter which antiderivative we use. Good job, Theo. Okay. So here's our antiderivative according to the second part of the fundamental theorem. All I have to do to find this integral is take 6x, well, okay, let me write the whole thing. The integral from -2 to 3 of 6 with respect to x is equal to 6x. Evaluated at this line means I'm going to plug in the following numbers. Evaluated at 3 and -2. And then that's equal to, okay, I plug in 3, 6 times 3, minus, I plug in -2. And then whatever number that is, that's your answer. So that would be, I guess, 18 minus -12, so plus 12, which is 30. Okay, that was an interesting point that Taeyeon brought up, so let me say a few things. What he was saying is that 6x gives me a derivative of 6, but also 6x plus 11, or 6x plus 3, or 6x plus any number also gives me a derivative of 6. So you might be wondering, okay, so wouldn't that change the answer if you use 6x or 6x plus 46? The answer is no, because you don't have to write this. This is just to show you why it doesn't matter. If you had used like 6x plus 46 and plugged in your numbers and everything, what happens is you do 6 times 3 plus 46 minus, then you plug in your other number, 6 times negative 2 plus 46. And then you end up with a 46 minus a 46 cancels, and then you get the same thing. So it doesn't matter. Yeah, that's good thing. What else was I going to say? That was important. Oh, yeah, okay, just another thing to connect it back to what we already know. This particular integral we could have gotten without any fancy math, without the fundamental theorem, because remember this function 6 is just a straight line, horizontal. So like right here, that's that function, it's a horizontal line. So if we're trying to get the integral from negative 2 to 3, you could just get the area of this rectangle. Okay, and so that's a good way to check our answer if we did it correctly. The area of this rectangle would be 5 times 6, 5 for the base, 6 for the height, which is 30, which is what we got. Sweet. All right, cool. So there's the fundamental theorem. You find an antiderivative, you plug in your stuff. Okay, so what if your function is a little bit trickier? Find the, or evaluate the definite integral from 0 to 3 pi over 2 of cosine of x. Okay, all right. So again, you have to think, what did I have to take the derivative of to end up with cosine? Nice, nice, nice. Good job with the positive sign. Yeah, all right. So remember, the derivative of cosine is negative sign, but that's not where you're thinking backward. So what did I have to take the derivative of to get positive cosine? That had to have been positive sine. Is an antiderivative of cosine because the derivative of sine of x is cosine of x. So according to the second part of the fundamental theorem, this integral from 0 to 3 pi over 2 cosine of x dx is exactly equal to the antiderivative, which is sine, and then evaluated at these limits of integration. So sine of 3 pi over 2 minus sine of 0. Okay, all right, you guys remember your unit circle? You guys remember what sine of 3 pi over 2 is? 3 pi over 2 is the one down here. So the y value would be what? Yeah, all right, okay. Yeah, this would be negative 1, and then minus sine of 0, that's this one right here, so the y value would be 0, so sine of 0 would be 0. All right, so here's your answer. Negative 1 minus 0 is negative 1. Cool, 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 very cool. All right, and then in terms of areas, what does this mean? Well, remember, cosine looks like a wave like this, where this point is 3 pi over 2. So the area between 0 and 3 pi over 2 is this area. And yeah, it should make sense that we got a negative area because there's more area that's under the x-axis than above it. So like this stuff all cancels out with this stuff, like halfway through here, and then all of this has an area of negative 1. Cool. All right. What else is there? Oh, tables. Okay. So this says the selected values of a twice differentiable function f and its derivative f prime are shown in the table above. Evaluate the integral. Okay, all right. Okay, yeah, I mean, there's not much for me to say. We just found out using the second part of the fundamental theorem that this integral is equal to the antiderivative of f prime. In other words, well, I don't know. I don't even know if I can put it in other words. The antiderivative of f prime would just be f, because if I take the derivative of f, I get f prime. Okay, so this would be equal to at normal f of x evaluated at 1 and at negative 3. Okay, so you plug in your points and that's it. Okay, so f of 1 minus f of negative 3 table. F of 1 is 3 minus f of negative 3 is 6. I'm just reading these two guys. And then that's it. 3 minus 6 is negative 3, and that's your answer. Cool. Yeah, you didn't need to know a lot of this information, really. You didn't need that it was twice differentiable at all. Well, I guess you kind of did behind the scenes, because twice differentiable means that the derivative is continuous, so you can apply the fundamental theorem. But that's the only reason. Okay. Okay, then this one, it requires a tiny bit of thought. Watch this. The graph of f prime, this is the graph of f prime, is given below. If f of 7 is 5, then find f of 15. Okay, all right, okay. So the reason this takes a little bit of thought is because you have to go like this. I want to know something about f, normal f. The only things I know, though, are things about f prime, or the only, like, graph or reference that I have is for f prime. Okay, so that should tell you, all right, well, I want to go backwards. I want to, like, undo a derivative. That means I got to integrate. Okay, and then if I want to integrate f prime, then I should have limits of integration. And the only two numbers I know anything about are 7. So I should go from 7 to maybe where I'm interested in, 15. Okay. And then this should get us to the answer, but it won't be exactly the answer. Okay. Because, watch this. If I were to take this integral, we just learned that the, like, answer to this, this integral evaluates as, well, I undo the derivative. In other words, I get f back. And then I plug in 15 minus f of 7. That's not exactly what I wanted. I don't want f of 15 minus f of 7. I just want f of 15. But okay, that doesn't matter. I can just solve for f of 15 by adding the f of 7 to both sides. Okay, so here's me adding f of 7 to both sides and writing it in a more normal way. We put the f of 15 this way would be equal to f of 7 plus this. And then now I have what I want. You guys see what I just did, or no way? And why I did everything? Okay, all right. Okay. I have an intuitive way to explain this as well, but is that, like, I don't know. When you first learn the fundamental theorem, I don't know. It's not super, you'd have to spend time thinking about what I said for a while. But I'll explain this in an intuitive way in a second, but it's still not going to be, like, super understandable until you think about it for a little while. Okay, so I want f of 15. I know that f of 7 is 5, according to this. So f of 15 would be equal to 5 plus this integral. Okay, but that still leaves this integral. How am I going to do this? How am I going to find out what number that is? You guys know it. I know you do. I have this graph. Yeah, what do you think? Yeah, it's an area. Remember this? That's all this means. Get the area between 7 and 15 under this graph, which I have. I have the graph. Cool. Okay, so let's get this area. That would be, here's 7. That should be a straight line. 7 to 15, which is here. Okay. So I need to get this area. Okay, and then add 5, and then that's it. Okay, so let's do that real fast. That would be 5 plus All right, that area, it looks like a triangle and a trapezoid. So the triangle has an area of 1/2 base, which is 2, times height, which is 20, according to the graph, plus the area of that trapezoid. And then normally I don't remember the area for a trapezoid, so I would split this into a triangle, or like, sorry, 2 triangles and a rectangle. But since I just taught the area of a trapezoid, I have it fresh in my mind. That should be the height of this trapezoid, which is -10, times the first base, which is, 9 to 15 is 6, plus the second base, which is 10 to 14, is 4 over 2. All right, nice. And then whatever number that gives you, that's your answer. So let's check. Well, we could just do it ourselves. This would be 5 plus 20 minus 10 times 5 minus 50, which is -24. So f of 15 is -25. Is that what I got? Yeah. Cool. All right, now let me explain this. Okay, so first of all, if this made sense and you don't care about so much about the reason why this works, all right, you don't have to listen that hard. But let me try to explain this in an intuitive way so that you like know why everything is working. Okay, so first thing is that we just learned this fundamental theorem of calculus. Okay, which tells you basically that if you take the integral of something, you are getting the total change of a function between b and a. So the total amount of change that f is changing, yeah, the total amount of change for f between b and a. Okay, so if I'm trying to find out what f of 15 is, in other words, where my function is at x equals 15, then what I could do is find out where did I start, where was I at 7, and then add up the total change between 7 and 15. So that's what this is. Where was I at 7 plus how much did I change in total from 7 to 15? That's the intuitive definition, or like the intuitive explanation. But like I said, the first time you hear that, it's like, I don't know if it fully clicks. So spend some time at home if that didn't make sense. Think about it, and then it should make sense. Or ask me after class, or watch this video again. All right, that's that one. Questions on it? Okay, and then here's the last thing. Here's the first thing we're teaching you about your calculators is that they can do integrals like straight up in your calculator. So if you have a TI-84 or a TI Inspire or whatever you guys have, here's how you can take integrals. So here's an example, and mine might look different from yours. This is a school calculator. It might not be as updated as yours. But let's say I wanted to take that integral that's in your packet, e to the x from 2 to 9. Then what you can do is hit this math button, and then go down, or you can just hit 9, but you can go down to 9, and then that says function integrate. Notice there's also a derivative one, for if you're ever trying to take a derivative at a point. In this case, we're interested in integrals. And then a lot of your calculators, if you're just getting them like recently, they will actually have the little symbol. So they will look like this will come up, and then it's a note. You just fill in the numbers that you want. But if yours comes out like this, then you have to fill it in a special order. Just in case any of you have it, that would be like this: e to the x. So you do your function e to the x. You want to integrate that with respect to x, so you do a little comma x, and then you tell it from where to where. So comma 2, comma 9, and then it gives you the right answer, 80, 95, which is what? the thing says. Cool. So your calculators can take integrals. That's nice. All right. With that information, now we can complete example 10, which says let g be a differentiable function such that g of 8 is e and g prime of x is that function. What's the value of g of 3? Okay. So that should look really, really similar to the last one. It is like the exact same setup. If I want g of 3, and I only have stuff about the derivative, then I should be integrating that derivative. So, okay, take the integral of 3e to the negative x dx. All right, cool. And then you have some choice about how to set this up. You could, if you like get more experience and you see it this way, you could set this integral up from 8 to 3 so that it matches exactly the same setup as up here. Look at how here we wanted f of 15 and we knew something about f of 7. So our bottom limit was 7, our top limit was 15, so that we could end up with this formula. All right, you could do the exact same thing down here. But it's not very intuitive to set up an integral backwards, going from 8 to 3. So most of you probably would say, oh, let me go from 3 to 8, and there's also a way to do that. That's fine. Okay. And so this, remember, according to the fundamental theorem, would give you g of 8, because this was g prime. G prime is this. So this would give you the antiderivative g of 8 minus g of 3. And then you can solve for g of 3. So if I want g of 3, that would mean I could just add g of 3 and subtract this over. So let me do it one thing at a time. That means that g of 3 plus this integral is equal to g of 8. And if I want just g of 3, then I can subtract that integral over. So g of 3 equals g of 8 minus this integral from 3 to 8 of 3e to the negative square root of x dx. Cool. And then we know what this is. We can find out what this is using our calculator, and that gives us g of 3. All right, so that implies that g of 3 is equal to g of 8, which was e, minus whatever this integral is. So let's find out what that integral is. Okay, according to my calculations, the integral of e to the negative square root of x with respect to x between 3 and 8 I missed the parenthesis, is that much. What did I do wrong? Maybe nothing. Maybe I just did it wrong originally.
You put up with 3, right?
No, I have this.
The 3e.
Oh, that's what it is. Good job. Good job. Thank you. Yeah, you're right. It was 3e to the whatever. And then, okay, that looks more familiar. All right, so then I get 1.54245. Remember that the AP test, if you care about this, cares about up to 3 decimal places. So what I like to do is be safe and go to 4 and then just truncate. Like, not worry about rounding or anything, and just go to 4 and then stop. So 15424. Okay, 15424, 15424, 15424. Now I have g of 3 equal to this, and then that's my answer. Nice. All right, very cool. Okay. And then that's it, I think. Yeah, that's 6.4. So we'll do that Monday, I think, or whatever, Tuesday actually. Tomorrow will be a work day. If you care, let me show you this other thing. So had you set this up from 8 to 3, that would have been nice because then you can use the same exact formula from the last one. Like you could do starting point plus the total change will give you the place where you end. So that would be, you could have set it up also like this. G of 3 is equal to starting point plus total change 8 to 3 of your function with respect to x, and then you would get the same exact thing because notice plus this integral is the same thing as switching the bounds and subtracting. So same thing. All right, I think that's all I have to say. Good job. If you have questions, let me know. And then your homework is just the rest of your homework from last week.